Assalamualaikum and good day everyone. In this video, I would like to explain how we analyze indeterminate beam using flexibility method. We focus on two redundant in the system. Okay, this beam is A, B, C, D has fixed at A and supported by rollers at C and D. We need to use the flexibility method, determine reaction at supports, all supports. Okay, for question A, and for question B, if support D is settled by 20 mm downward, determine moment at support A. So there are two questions here. So question number 1, question A is the basic question, and question B is additional question whenever support settlement occur. Okay, so we will start with calculating the degree of indeterminacy. So degree of indeterminacy we will calculate from finding the difference between number of unknown reaction and three equilibrium equation. It is actually three unknown reaction that can be solved using three equilibrium equation. So we get 2 here. So we have to choose redundant, because redundant we need to remove from the system. Okay, so we have three options, but in this example I have chosen CY and DY as the redundant. So when we remove CY and DY together, we will have cantilever beam as the system to be analyzed later. Okay, and from the principle of superposition, so always remember the general equation. It is written as actual beam equals to primary beam plus redundant 1 plus redundant 2. And to be specific, we should write CY applied, redundant CY applied as redundant 2, and redundant DY applied, redundant 1, and redundant DY applied as redundant 2. Okay, and as we know, I have shown to you, we have already derived the compatibility equation from the principle of superposition in my previous video. So after understanding the procedure, so now we can straight away write the compatibility equation by always remembering the general equation. Okay, so we will write the compatibility equation, which is actually based on displacement at redundant position. It is displacement at redundant position in each system. There are three systems, three determinate system to be analyzed. The first one is primary beam. Second one is redundant 1, redundant CY applied. And third one, redundant DY applied. So we write the standard form of compatibility equation. We start with the primary system first, and then we plus with redundant system. Then only we equal to 0, because in actual beam there's no movement. In actual beam, because of roller at C and D, there's no vertical movement. So this equation is equal to 0. Okay, so from the compatibility equation here, okay, it is delta 1 not delta 2 not, delta 1 not delta 2 not. So always remember that the first notation is for the position, and second notation is for type of beam, type of structure. So this is for redundant 1, redundant 2. Okay, means that this is for the primary system because the label is not. Okay, then for redundant system, we group together all displacement. There are two redundant, so we will have 2 by 2 matrix, 2 by 2 matrix written using metric characteristic. It is 2 by 2 matrix. So we write F for flexibility coefficient representing displacement. It is F11, F12, F21, F22 times with CY and DY. CY is redundant 1, DY is redundant 2, equal to 0. Okay, inside this compatibility equation, we can see there are three symbols used here. It is 0, 1, and 2. 0, 1, and 2. And since this is beam, so for beam displacement, we integrate to get displacement. We integrate moment equation to get displacement. So we should understand that we will have to analyze moment equation. From three system, we will label as M0 for primary beam, M1 for redundant 1, redundant BY applied, and M2 for redundant 2, redundant CY applied. So there are three systems to be analyzed.